Today we're going to talk about rational functions. When you see the word rational, you should also see the word ratio inside that word. And when you think of a ratio, you think of one thing being divided by another. And that's exactly what you're going to get when you're working with rational functions. So a rational function takes this form, p of x over q of x, where this p and this q, they're polynomials. And the bottom polynomial is not the zero polynomial. So let's review really quickly what a polynomial is. So p and q take this form. P of x is a sub n times x to the power n plus a sub n minus 1, x to the n minus 1, and so on. Where this a sub n minus 1, those are your coefficients. And in this particular example, and the examples we're going to see, all of these coefficients are real. And this number here, n, is your degree. It's the highest power on the x, and this degree is a non-negative integer. So it could be 0, 1, 2, 3, and anything like that. So no fractions, no negative numbers, just whole numbers. Same thing for q. Q is also a polynomial. It just can't be the zero polynomial. It doesn't have to have the same degree as p. It can have a different degree. Again, these are all real numbers. And yeah, so this degree is a non-negative integer. So let's look at some examples of rational functions, just to get a feel of this. So our first example is f of x is equal to 3 minus x over x squared plus 1. Notice that the degree on the top polynomial is 1, and the degree of the bottom polynomial is 2. Here's another example. G of x is 12x to the 4th minus 3x squared plus 1 over x to the 9th minus 7x plus 4. The degree of the top polynomial is 4, and the degree of the bottom polynomial is 9. Another example we can put up here is just a polynomial, like 7x to the 5th minus 3x squared plus 8. Why is this a rational function? Well, notice that if you take this polynomial and you divide it by 1, you get the top polynomial. So the number 1 is a polynomial. It's equal to, you could say 0x to the 1 plus 1 times x to the 0, or in other words, it's just a constant. So this 1, the degree is 0 here. So it's just the constant polynomial 1. So that is also a rational function. Let's look at some non-examples. So here are two good non-examples. F of x is the square root of x plus 1 over x cubed minus 3, and g of x is x to the negative 5th plus x squared over 1 plus x. What's wrong with the first one? Well, if you ever see square roots, if you see a function like this one on the top with a square root, it's not a polynomial. As long as it's square, if you have a square root in the coefficient, that's fine. But if you have an x underneath that square root, it's not a polynomial. So this doesn't follow the fact that the top one is a polynomial. So it's not a rational function. The second one has a negative power with this x. So that is not a polynomial function either, because remember, the powers can't be negative. Here's a very important rational function that we actually learned about a little bit a while back when we were memorizing functions like parent functions, and we were learning how to manipulate those parent functions to look like another type of function. So for example, when we had f of x is equal to x squared, and we had to graph something like g of x is x squared plus 3, we had to know what this function looked like, and then we moved it up 3, so we did some transformations of graphs. Well, this function, let's call it f of x is equal to 1 over x. That was one of the functions we had to memorize, like the graph of this function. So we're going to review that function, talk about its graph, and then we're going to look at some more complicated rational functions. We're going to learn about some aspects of the graph, and then eventually what we want to do is we want to learn how to graph these rational functions. So let's start with this one. F of x is 1 over x. Now let's remind ourselves what this function looked like. So I'm going to do a really quick sketch. Okay. So if you recall, and I'm going to also graph this on like a graphing calculator so you can see it a little bit better. But if you recall, this graph has two pieces. This is one of the pieces, and here's the second piece. So this is a smooth graph. So there's no real sharp turns, but these edges here, when I turn like this, I have nice rounded edges. I could plot some points if I wanted to. For example, if I plug in x is equal to 1, I get f of 1 is 1 over 1, so it's just 1. So I have the point 1, 1 on the graph, which is right here. And I could choose stuff that's smaller than 1 to plug into the function, like 1/2. Watch what happens when I plug in 1/2 into this function. Well, I get 1 over 1/2, which is 2. So at 1/2, I'm up at 2. And in fact, if I plug in 1/3, which is a little bit closer to 0, I'm at 3. And so on. So you can see that the closer I get to 0, the bigger the y value is going to be here, this function's value. And so we're getting closer and closer to 0. So we're getting closer and closer to this line here. Also, if I plug something really big in, so let's say I let x equal 2. If I plug that into my function, I'm going to get 1/2. So I go 2 and then halfway up. So this is 2, 1/2. And if you plug anything bigger than 2 in there, so if you plug in 4, you'll get a 4th and so on. So this part of the graph is getting closer and closer to the line y is equal to 0. We could talk about this side as well by plugging in negative numbers. Notice you can't plug in 0 because 1 divided by 0, that doesn't make sense. It's undefined. So that's why we don't have any y-intercepts here. If we plug in -1, you're going to get the point -1, -1 here. And you're going to have something similar happening if you plug in something smaller than -1 that's closer to 0, like -1/2, then you'll get -2. So like this point is -1/2, -2. And if you plug in -1/3, this will become -3, and you can see that you're going to get closer and closer, but in this downward fashion to the line x is equal to 0, which is this y-axis. Now, if you plug something, I guess you could say more negative, like if you plugged in -2 into here, you'd get -1/2. So you can see that the y values are going to get closer and closer to 0. The big, I guess the more negative you plug into the function. So if like you plug in -3, you're going to get -1/3. -4 is going to give you -1/4 and so on. So you can see that this line is going to approach 0. Now this is something called an asymptote. This straight line here, this is called a horizontal asymptote. Let's write down the equation for this horizontal asymptote is y is equal to 0. And I'm going to teach you how to find that in just a second. We also have something called a vertical asymptote, which is just a straight line here. This is our vertical asymptote. That is the line x is equal to 0. And that has to deal with this, this polynomial in the bottom here. So I'm going to write a few things down. The first thing I want to write down is, let me erase this so we have some space on this side. Just some things we notice about the graph. So as x approaches infinity, what is happening? So remember that this is your x line right here. And here's 1, here's 2. And as we're getting bigger and bigger, going towards infinity, this function, remember this line that we've drawn is our y values. And we said as we get bigger and bigger, so if I plug in 3, I get a 1/3. And if I plug in 4, I get 1/4 and so on. If we plug in something really large, the value we're going to get is going to be very small and really close to 0. So as x approaches infinity, what's going to happen is your function is going to approach 0. You're going to learn in calculus that this is called a limit. And what they'll write is the limit as x goes to infinity of our function is equal to 0. Now also, we could talk about going towards negative infinity. So if we go in this direction, so -3, -4, -5, again, we're having something similar happen where we have a negative number. So if I plug in -5 here, I get 1 over -5. And if I plug in -6, I'm going to get 1 over -6. If I plug in -100, I'm going to get 1 over 100, which is a very small negative number. It's getting really close to 0. So something else you could say is as x goes towards negative infinity, then our function is going towards 0. So it's approaching 0. The further we go out this way with our x values, the closer this line is getting to 0. And that can be written as the limit as x approaches negative infinity of f of x is equal to 0. Okay, that brings me to the definition of a horizontal asymptote. So we're going to write that definition down here. So a horizontal asymptote is given by the following. If, as x approaches infinity, or x approaches negative infinity, the function, now of course it depends on what your function's defined as. Here we're defining as f of x. The function f of x approaches some fixed number L, then the line y is equal to L is a horizontal asymptote. So I'm going to say it's called a horizontal asymptote. So as you can see, again, it's going to be a horizontal line that your function, at least on one side, it doesn't have to be both, but on one side is going to approach as x gets larger or as x gets more and more negative. So going out to negative infinity. So horizontal asymptotes determine the end behavior of your graph. Now you can intersect a horizontal asymptote. It's just that as you go out towards either negative infinity or positive infinity, you approach that horizontal line. So we're going to write here that it determines the end behavior of our graph. And then we're also going to say we can cross a horizontal asymptote. I'm going to abbreviate it to HA. Okay. So let's go back to our graph here. Now let's define a vertical asymptote. So let me erase this right here. I'm going to do something very similar. I'm going to look at what happens when we approach 0. So as x approaches 0, and I'm going to put a little positive here from the right. So what we're doing, here's your x values. Okay, I'm going to erase this so this doesn't get us confused here. So here I have the number 1, 2, 3, and so on. As we go this way, going towards, here's 0, right, on the x line. As we go towards 0, what is happening? And so notice that we're going from the right. So here's 0, I'm coming in from the right. As we go towards 0, what's happening to this function? This function is approaching infinity. You can see that is we plug in something very small, like let's plug in 1 over 10, this becomes 10. If we plug in 1 over 100, this becomes 100. So as x approaches 0 from the right, this is going up, 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 and is going towards infinity. Then our function is approaching infinity. But notice what happens as x approaches 0 from the left. So this negative sign means that we're coming in from the left. So here's 0 again. Here's -2, -1. As we go this way from x going towards 0, our function is getting closer and closer to this line right here. But as we approach this, as we come in this way, this is going towards negative infinity. It's going to get really close to this line, but this graph is going downwards. So then f of x approaches negative infinity. Okay, when that happens, we have something called a vertical asymptote. Let's give the definition right here. So vertical asymptote if as x approaches c, which is some fixed number c. Now from the left or the right, but as you approach it, then f of x approaches infinity, or f of x approaches negative infinity, then the line x equal to c is a vertical asymptote. So it's called a vertical asymptote. And let's go back up to our picture. Our picture here, as we approached 0, one side was going towards infinity when we were coming in from the right, and as we were coming in from the left, this side was going towards negative infinity. Now they could both go up towards infinity, or they could both go to negative infinity, or they could go in different directions. As long as you don't cross this line, you're not going to cross a vertical asymptote. You can cross a horizontal asymptote, but not a vertical asymptote. So it's a line that you're getting really close to, but you don't touch. That's a vertical asymptote. So our vertical asymptote here is x is equal to 0. Okay. I also want to mention, I'm going to put it right here, that we cannot cross a vertical asymptote. Okay. A few other things I want to mention about this particular graph is the domain and the range. So let's talk about that real quick. So what is the domain and what is the range of this function? Sorry, this should be range. So the domain is all the x values that you cannot be. And we don't even have to look at the graph to figure this out. We just have to look at the original function. Remember, when we have fractions, so we look at this function and we ask ourselves, what's the numbers or number that we cannot plug into this function? We'll get some kind of error. And notice that the only number that you can't plug in is 0, because we can't divide by 0. You can divide 1 by anything you want to except 0. So x cannot be 0, which means the domain is negative infinity to 0, union 0 to infinity. And you can see that from the graph as well. Remember how we tell the domain from a graph. We look at the x line, and for every x value, like this one right here, we look and see if there is a point on the graph that corresponds to it. So for every x value, we have something. Even if we get really, really close to 0, way down here, this graph is going to go on forever, and it's going to kind of go towards the right. But we won't have a value for 0 because we're never going to intersect this vertical asymptote. So you can see that the parts in our domain where we have an issue, those will become vertical asymptotes. Okay. Now let's talk about the range. The range isn't something that you can just see from the graph, the function here. You have to look at the graph. So looking at the graph, I'm going to erase this stuff because it's a little cluttered. But if we look at the graph, remember that the range is how far up and down we go. Notice that at 0, for anything above 0, let's say right here, we're going to have a point way out here. If we get really close to 0, we're going to have some point way down here. But if we go up, we're always going to have a point. So we're definitely going towards infinity and also towards negative infinity. But for this particular function, we're not going to intersect this line. We're not going to have any x-intercepts. So the range for us is anything but 0. So it's negative infinity to 0, union 0 to infinity. Again, with the range, we have to actually look at the graph. Okay, so let me tell you how we're going to determine if we have vertical asymptotes and horizontal asymptotes just by looking at the function. Okay, so we're not going to look at the graph. The idea is eventually we're going to graph these, but we can actually get that information if we have a vertical asymptote or horizontal asymptote just by looking at this function. Okay, and this is what we're going to do. I'm going to write it down here. So those definitions I gave you, this helps you find a vertical asymptote and a horizontal asymptote by looking at the graph. And we're going to do that as well. But I'm going to give you some formulas for finding horizontal and vertical asymptotes just by looking at the function. Okay, so let's write it down here. Okay, so given a function f of x, let's say is equal to p of x over q of x, simplify the function as much as possible. And what I mean by that is, if you can factor the top and the bottom, factor it. And if they have a common factor, so for example, let's say you have x minus 3 times x plus 1 over x plus 1 times x minus 4. Let's say you had two functions, top function and the bottom function, and you factor them and you got this. What you want to do is you want to get rid of any common factors, just like that. Okay? When you do that, this bottom part right here tells you what your vertical asymptote is. Here, x cannot be 4. So we cannot plug 4 into the function. So notice x is not equal to 4, which tells us that we're going to have a vertical asymptote at x is equal to 4. That is going to be a line. This is a value we cannot plug in. This is the equation of a line that gives us a vertical asymptote. Okay, so any value c that when you put this function into lowest terms, if it's a 0 of the denominator, so like this number here would be 4, 4 is a 0 of this, then you have a vertical asymptote. So let me write that here. So you want to simplify the function as much as possible. any value C that is a real zero of the denominator, which means x minus c is a factor of the denominator, gives us a vertical asymptote at x is equal to c. So we're going to look at plenty of examples of this, so don't worry too much about it. Just know that when we take a rational function and we want to find the vertical asymptotes, we factor, we get rid of common factors if there are any, and then what we have left over, we look at the bottom, and if we have things that when we plug, if we have numbers that when we plug them into the bottom, we get 0 in the bottom, then those will correspond to vertical asymptotes. Also, I want to mention that when we want to figure out the domain of a function, we're going to look at the function before simplifying it. So if this is a function that I give you, of course, if you cross these out, this tells you where your vertical asymptotes are. Before I cross them out, I do have a problem where I can't plug this into the denominator, this -1 here. If I plug in -1, I get 0 here and 0 here. That's going to correspond to something called a hole. We're going to have a hole in the graph. I'll talk about that more later, but that's the point we're going to have to take out of the domain. So when I give you some more examples, we'll talk about holes later. Okay, so how can we tell if we have a horizontal asymptote? So let me just make some space here. So how to find horizontal asymptotes? Just by looking at the function if the degree of the numerator is less than the degree of the denominator, then you will have a horizontal asymptote at y is equal to 0. So no matter what you have for the top polynomial, whatever you have for the bottom polynomial, if the degree of the numerator is less than the degree of the denominator, you're always going to have a horizontal asymptote at y is equal to 0. Now, let's say, what's going to happen if the degree of the numerator is equal to the degree of the denominator? You will have a horizontal asymptote as well. So I'm going to write here, let r of x equal p of x over q of x, where, because these are polynomials, p of x, let's say this is a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on. And let's say q of x has the same degree. So it's b sub n x to the n plus b sub n minus 1 x to the n minus 1, and so on. And the reason I'm using a different letter here is because I don't want the coefficients to necessarily be equal, but I want them to have the same degree. Okay? So if the degree of the numerator, so p of x, is equal to the degree of the denominator, then you will have a horizontal asymptote. At y is equal to a sub n over b sub n. So you're just going to take those two leading coefficients and divide them, and that will give you your horizontal asymptote. Of course, we can talk about when the degree of the numerator is greater than the degree of the denominator. We're going to leave that for later, but right now we just want to focus on when the degree of the numerator is less than or equal to the degree of the denominator. That's going to give us horizontal asymptotes. Okay, so let's look at some more examples. So also, if we go back up to this problem we just did, notice that the degree of the denominator is 1, the degree of the numerator is 0. So we have a horizontal asymptote at y is equal to 0, which is what we saw when we drew this, at y is equal to 0, because the degree of the denominator is bigger than the degree of the numerator. Okay, this is in simplified terms, so we can't factor the top and the bottom, cancel anything out. So at the bottom, we cannot plug in 0, and that's why we had a vertical asymptote at x is equal to 0. Okay, let's move on to another problem. Okay, here we are. R of x is equal to 6 divided by negative x squared plus x plus 12. What I want to do is I want to find the domain. Let's put that here. What's the domain? What are the vertical asymptotes, if there are any? I'm going to put a question mark here. And what are the horizontal asymptotes, if there are any? So to find the domain, remember that the domain is all the numbers that we cannot plug into the function. What we're going to do is we're going to factor the denominator. So we have negative x squared plus x plus 12. How can we factor this? First thing I'm going to do is I'm going to take out this negative. Then I'm going to focus on this trinomial. I need two numbers that multiply to give me negative 12 and add to give me negative 1. They happen to be negative 4 and positive 3. So this factors into negative x minus 4, x plus 3. Remember, as long as the coefficient in the front of x squared is 1, you can just break it into x plus this number and x plus that number. So what I'm going to do is I'm going to write this. This is the same thing as 6 over negative x minus 4 times x plus 3. Always get it in this nice factored form. Okay, so looking at this, what numbers can we not plug in the denominator? How will we get a 0 in the denominator? Well, if we plug in 4, or if we plug in negative 3, we're going to have a problem. So for the domain, x cannot be 4 or negative 3. If we want to write that in interval notation, we would say the domain is anything from negative infinity. Remember, interval notation, you start with the smallest number and then work your way up. So the smallest number between these two is negative 3. Then we're going to we're going to get all the numbers from negative 3 to 4, union, and then go from 4 to infinity. We have to take these two numbers out. Okay, so the domain is anything but those two numbers. For the vertical asymptotes, so here we have our completely factored form. The places where we have problems in the domain in the completely factored form is where we're going to have vertical asymptotes. So we're going to have two vertical asymptotes. And they're going to correspond to x is equal to negative 3 and x is equal to 4. Now these are going to be straight vertical lines. As for horizontal asymptotes, we need to figure out the degree of the numerator and the degree of the denominator. So let's write that here. The degree of the numerator, well, the numerator is just the number 6. It doesn't have any x's. You can think of it being multiplied as x to the power 0. So the degree is 0. And the degree of the denominator well, let's go back to this unfactored form. You could look at this one as well if you factored it, if you expanded it. You can see that this degree is 2, and that the degree of the denominator is greater than the degree of the numerator. Because of that, we're going to have a horizontal asymptote at y is equal to 0. So all of this is important information. It's going to tell us a lot about the graph. Eventually, we're going to use it to graph the function, and we're going to just start breaking this up so we can have an idea of what to expect with this function. So what I'm going to do, I'm trying to zoom out a little bit. Over here on the side, I am going to make a plane. And I'm going to put these pieces of information out. So we have a vertical asymptote at -3. So let's go out 1, 2, 3. I'm going to put a dotted line here. So this is x is equal to -3. And then also at 4. So 1, 2, 3, 4. I'm going to put another dotted line. This is x is equal to 4. And then I'm going to put one more dotted line that corresponds to this horizontal asymptote, y is equal to 0. So right here. This is y is equal to 0. So you can see that what we've done is we've broken the plane into 1, 2, 3, 4, 5, 6 different places. And something's going to happen when we draw this graph. We're going to get asymptotes. So we're either going to have on this side of the graph, because this is a horizontal asymptote, it tells us end behavior, it tells us what happens as x goes to infinity. Either we're going to have something like this or like this in our graph. Same thing on this side. It's either going to look like this or it's going to look like this. So you're going to have your graph approaching infinity as your function goes towards infinity. You can see it's getting closer and closer to y is equal to 0, this horizontal asymptote. And it's going to happen over here as x goes towards -infinity. Your graph is going to do something like that, go towards y is equal to 0. And then in the middle, or right here as well, you have these asymptotes. So what's going to happen is your graph is going to go up towards this asymptote, or maybe it's going to go down towards this asymptote, but it's not going to cross it. And then in the middle, you might have something like where you're going up towards this asymptote and you go down towards this one, or you're going to have maybe the same thing happening down here. Again, I mentioned that you can cross a horizontal asymptote, so you might have something like this. But what you want to notice is that you have asymptotes. It's breaking the plane into several pieces, and that at these asymptotes, your graph is going to go towards them, like this one here. It's going to go up towards it, or maybe down towards this asymptote. Same thing on this side. So you might go up like this, or maybe down. And then you're also heading towards these asymptotes. So now I'm going to graph this function and see which one is correct, what's going to happen here. So I'm going to put this into Desmos. So let me share my screen here. Okay. I'm going to put r of x is equal to 6 over -x squared plus x plus 12. And now let's look at this graph. Okay, so these asymptotes, these dotted lines that I gave you, they don't show up in the graphing calculator. They help us sketch the graph, but they're not going to show up because they're actually not part of the graph. They just help us make the graph. But notice a few things about this function here. Let me zoom out some. So you can see if I touch this graph, if I get close to, remember one of the asymptotes was -3. So as I get closer and closer, here's -5, here's -4. As I get closer and closer to -3, look what's happening. You can see on the left, on the points over here, the x value is getting closer and closer to -3, but the y value, you can see, is going towards -infinity the closer I get to it. So if I zoom out, you can see that this is happening here. And then you can see on this side that, remember we had a vertical asymptote at 4. So as we get closer and closer to 4, so as x approaches 4 from the right, we're going towards -infinity. And then here in the middle, you can see that we're also right here where that asymptote was, which was at -3. As we get closer to -3 from the right, we're going towards infinity. And over here, as we get closer to 4 from the left, we're going towards positive infinity. Okay, and then you can see that this line y is equal to 0 is like an asymptote here. You can see that because you're getting really close to that line. If we zoom in, we can do a better job of seeing it. But you can see as we go out from here's 7, 8, you see the number, the y value is getting smaller and smaller and getting closer and closer to 0 because we're going towards that horizontal asymptote. And then on this side, we have a similar thing happening. Okay, let's switch back to this OneNote. So we saw that what actually happened was we had something like this. And again, we're going to learn how to sketch that later on.